Good morning, friends. Welcome to the next lecture of functional analysis. In today's lecture, we are going to see two important theorem, which is known as Riesz lemma and Riesz theorem. Those are very important theorems in Banach spaces and important from the point of view of examination as well. Okay, let us proceed. Let me share my screen. Okay, in the last lecture, we have seen the corollaries which are dependent on the theorem. All norms defined on finite dimensional nonlinear spaces are equivalent, and from this we have proved an important theorem that if the domain of a linear mapping is finite dimensional, then the mapping is continuous also. Now, in today's lecture, we are going to study Riesz lemma. Riesz lemma. Okay. Now, first of all, we'll try to understand about something about the mathematician Riesz. Let me show you here. Yes, Frigyes Riesz was Hungarian mathematician. The life tenure is 22nd January 1880 to 28th February 1956. He has made the fundamental contributions to functional analysis. Okay, the same contributions are also made by his younger brother Marcel Riesz. As we can just have an overlook on his life, he was born into a Jewish family. Okay, between 1911 to 1999, he was a professor at Franz Joseph University in Kolozsvár, Austria-Hungary. Then he has transferred from Austro-Hungarian territory, including Kolozsvár, and whereupon Kolozsvár name changed to University of Kolozsvár. Okay. Similarly, Riesz did some fundamental work in developing functional analysis, and his work had a number of important applications in physics. He established a spectral theory for bounded symmetric operator in a form very much like that now regarded as a standard. He also made many contributions to the other areas, including ergodic theory, topology, and he gave an elementary proof of the mean ergodic theorem. He founded Acta Scientificarum Mathematicum journal together with Alfred Hare. That is, he started a journal to publish the research paper. He had an uncommon method of giving the lectures. He entered the lecture hall with an assistant and a docent. Docent had begun reading the proper passages from Riesz's handbook, and the assistant wrote the appropriate questions on the blackboard, while Riesz started himself stood aside, nodding occasionally. Right. This is what somewhat life history about mathematician, Hungarian mathematician Riesz. Okay. Now we'll come to our lecture. Now today we will try to understand Riesz lemma. The statement of the lemma is here let Y be a closed proper subspace, is a closed proper subspace of a normed linear space X, epsilon be a real number lies between 0 to 1, then prove that there exists an element or a vector x naught in X such that norm of x naught is equal to 1. Norm of x naught is equals to means the vector is lying on the unit sphere, and norm of y minus x naught is greater than epsilon for all y in Y. This is what a statement of a Riesz lemma. Okay, this Riesz lemma will help us to prove the main theorem, which is called as the Riesz theorem. Right. To start up with the proof, we should make use of the concept to find out the distance between a point and a set. As already we have discussed previously, that to find out the distance between point and set, we have used the concept of inferior. Okay, now here y is given to be a proper closed subspace of x, means there exists at least one vector or an element which is present in the set x minus y. In x minus y means it is present in x but not in y, that is in y complement. Okay, means somewhat like the situation we are discussing here. Suppose this be a proper closed subspace y of a normed linear space x, then we want to prove the existence of a vector x naught. This vector is having a norm value, that is length 1, means this vector is lying on a unit sphere, right? This is a unit sphere, though it doesn't look like a sphere, you please assume, right? Then this is, we want to prove that distance between any arbitrary vector y and this x naught is greater than epsilon, where epsilon is the value lying between 0 to 1. Okay, to give the proof of this part of the proof, we will assume that d is nothing but distance between a vector x1 and a subset y. x1 and a subset y. How to find out the distance between a point and a set? We know it was given by inferior. That is, we will find out the distance between x1 and all points of y, and whichever is giving us the infima value will be the distance between the point and the set. Okay, therefore we can define this as distance between x1 and small y, where small y is a vector in the subspace y. But as we are in the nonlinear spaces, the distance we will calculate with the help of norm. Therefore here let us write norm of x1 minus y on the condition y is in y. Okay, what is the job done? We will connect this x naught to all the points of y. Okay, we will find out the distance. Whichever is the distance we will get, whatever is the x1 vector we have selected. Say somewhere here is x1, right? Then we will join x1 with all points of y. Okay, then we will find out the distances. Whichever will give us the infima distance between x1 and the vectors of y will be the distance between the point and the set. Okay, which we are calling as d. Similarly, since y is closed, one can say d is greater than 0. Since y is closed, d is greater than 0. Okay, we will check why d is greater than 0, or what will happen if d is equal to 0. If d is equal to 0. If d is equal to 0 means what? There are some elements whose distance from a vector x1 is tending to 0. Okay, therefore I can say there exists a sequence yn in y such that, what such that? Norm of yn minus x1 will tends to 0. Okay, norm of yn minus x1 tends to 0. What it is giving us? The sequence yn is converging to x1. Okay, if sequence yn is converging to x1, then may I say x1 is limit point of y, limit point of the set y, but as y is closed, the set y will contain all its limit points. With that I can write x1 belonging to capital Y. But we have initially taken this vector x1 is in x, not in y, right? That is, it is in the y complement. Therefore anyhow d equals to 0 is not possible, is not possible. And as d is a distance, we know this is either greater or equals to 0. We are saying equal to 0 is not possible. Therefore the only possibility remains is d is greater than 0. Therefore as the subset y is closed, d is greater than 0. Okay, similarly as the epsilon value lies between 0 to 1, may I say d by epsilon is greater than d? D by epsilon is greater than d. Okay, now our aim is to construct a unit vector as it is in the proof. Our aim is to construct a unit vector, right? Now here, whatever is distance we have obtained, norm of x1 minus y, we have proved it is greater than 0. Therefore, let me assume there exists a vector y0, say, in capital Y, which is giving us a distance such that d is equals to norm of x1 minus y0. Means at a point y0, inferior distance between x1 and the vector holds, right? Therefore, this we are going to assume. Okay. Therefore, norm of x1 minus y0 is equal to d, and which is less than by d by epsilon. Okay, let me call this by some equation number 1. Therefore, as this is greater than 0, this vector is a non-zero vector. Therefore, why shouldn't I construct a unit vector with the help of this positive vector? How can we construct a unit vector from a given non-unit vector? The process is known to us. Just divide the given vector by its norm value. Therefore, what we will do? We will define a new vector denoted by x naught, say, as x1 minus y naught upon the norm of x1 minus y naught. Okay. Therefore, now what is the norm value of this vector x naught? Surely 1, because the vector x1 minus y naught is divided by its length. Or you can calculate norm of x naught. How can I calculate the norm x naught value? This is norm of x1 minus y naught upon norm of x1 minus y naught. But we know this norm of x1 minus y naught is a scalar. Therefore, we can take it out of the norm with a modulus. But as norm is already a non-negative quantity, no need to write down the modulus. Therefore, here norm of x1 minus y naught cancels, and we get norm value of the vector x naught is equal to 1. Hence, norm x naught is equals to 1. And where this vector x naught is going to belong? This x naught is belonging to x, no doubt. Why? Because this is a linear combination of vectors in x and y. Y is a subspace of x. That's why this total will be a linear combination. This total will be a linear combination of vectors in x. Therefore, this x naught must belongs to capital. Therefore, we have found one vector x naught in x with norm value is equal to 1. Okay. Now, second point to prove, norm of y minus x naught is greater than epsilon. Okay. Let us have a look what we have proved and what we are going to prove. Okay. This we have completed. Norm of x naught, we have found one vector x naught in x such that norm of x naught is equals to 1. Now the second thing is remaining to prove, norm of y minus x naught is greater than epsilon. To prove this, we will start with norm of y minus x naught. Okay. Okay. Therefore, let us start or consider. What to consider? For any y in y, for any y in capital Y, consider norm of y minus x naught. And our aim is to prove that this norm value is greater than epsilon. This norm value is greater than epsilon. Now let me write this as equal to y minus. What x naught we have defined just now? X1 minus y naught upon norm. Okay. Therefore, here let me write x1 minus y naught upon norm of x1 minus y naught. Let us complete the norm. Okay. Now come to the basic algebraic operation. Let us cross multiply and we will obtain the numerator as y norm of x1 minus y naught minus x1, negative of this negative, this will be plus y naught upon norm of x1 minus y0, right? Okay, now this norm x1 minus y0 used in this norm is a scalar. Therefore, let us take this scalar out of the norm with the modulus. But as I already told you, no need to write the modulus because itself is a non-negative quantity. Therefore, look at this term remaining. This is norm of x1 minus y0 plus y0 I will write. I will put everything in a bracket minus x1. Okay, therefore this is nothing but a distance between x1. Okay, and we will check what this is. This norm of x1 minus y0 is d. Therefore this is y into a scalar d plus y0. Okay, what is y0? Y0 is a vector in y. Y is also a vector in y. Therefore this bracketed quantity is the linear combination of elements in y. Here I will write y is in y, y0 is also in y, d is a scalar. Okay, therefore the bracketed term here is of the type y into d plus y0. Therefore this is a linear combination of elements in y. Therefore this must belongs to a subspace y. Okay, therefore we can say this is an arbitrary element y minus x1. Okay, one can change this as x1 minus an element in y also by taking a negative sign common. But what we have proved already, only for the element y0, d we have written norm of x1 minus y0 for y0 in y. Means for this vector y0 in y, norm of x1 minus y0 is d. D means it is the inferior distance. Then what for an arbitrary element in y? This inequality will be greater equal. Therefore, may I write norm y minus x0 is greater equal by this numerator is d upon norm of x1 minus y0. Norm of x1 minus y0. But previously in this equation number 1, we have proved that norm of here in equation number 1, norm of x1 minus y0 is less than d by epsilon. Therefore, if I take a reciprocal, what will happen? 1 upon norm of x1 minus y0, as we have taken reciprocal, it will be strictly greater by 1 upon d by epsilon, right? Therefore, here let us put the value greater equal. Now it becomes strictly greater by d by epsilon. Dd gets cancelled, epsilon goes to numerator. Therefore, we have proved that norm of y minus x0 is greater than epsilon for all y in y. For all y in y. Thus, we have proved both the things in the Riesz lemma, that for any proper closed subspace, if epsilon lies between 0 to 1, there exists a unit vector in X such that distance between y and x0 is greater than epsilon. This lemma will help us to prove the main statement of Riesz theorem. Okay, proof is very easy. The concept we have used to prove the result is this d. D is a distance between a point and a set, which is inferior among all the possible distances obtained by joining a vector x1 to the vectors in y. But distance in non-linear spaces are calculated by norm. Therefore, we have made this corresponding change, right? And then we have proved that there exists a, actually rather we have constructed the vector x1 minus, here we, by knowing norm of x1 minus y0 is equal to d, we have constructed a vector x0 which will be a unit vector, and the unit vector we have constructed by dividing this vector with its norm. Okay, then later with the simple calculations we have proved that norm of y minus x0 is greater than epsilon, right? Therefore, this is what about the Riesz lemma. Now we will go for proving the next, that is Riesz theorem. Riesz theorem. Okay. Let me just tell you what the Riesz theorem is. Okay, let us write the statement. Let X be a norm linear space. X be a normed linear space, and the closed unit sphere, the closed unit sphere. What is a closed unit sphere? Let us denote it by S. Is the collection of all vectors X in X such that norm X is equal to 1, is compact, then prove that X is finite dimensional. X is finite dimensional. Okay, therefore this is important because many a times we are interested in proving that the given space is a finite dimensional. Riesz theorem will give us a shortcut to prove the space to be a finite dimensional. What the theorem says that the closed unit sphere is compact, then it is closed bound, then the space is infinite dimensional. Okay, or statement can be written as if closed and bounded sets, closed and bounded sets are compact, in a normed linear space X, then it is finite dimensional. Then it is finite dimensional. Right? One can refer any one of the statement. Both are same. If you want to just check, let us have a look. Here it was given that the closed unit sphere is compact. But we know that this closed unit sphere is bounded as well. Therefore, if closed and bounded set, that is a unit sphere, is compact, then the given non-linear space is finite dimensional. Second statement also gives the same idea. That is, if the closed bounded sets are compact, then the non-linear space is finite dimensional. Before going to the actual proof, I just want to recall some basic definitions such as compact, totally bounded, etc. Okay, therefore coming to the basic definitions. Okay, first let me write down what is compact set. What is a compact space set, right? The metric space is said to be compact if it is both complete and totally bounded. Complete and totally bounded. Okay, now complete we know, many a times we have repeated the set to be complete, that every Cauchy sequence is converges to a point in the same set, then it is totally bounded, then it is complete. Sorry. Okay, now we will try to understand what is totally bounded. What is totally bounded? Okay, a metric space a matrix, suppose we have a metric space M, and a subset A of M is said to be totally bounded if, for given epsilon greater than 0, there exists finite number of subsets. Finite number of subsets. Let us denote it by some A1, A2, dot up to till AN of capital M, such that diameter of every subset is less than epsilon for all k is equals to 1 to n, and A is contained in union AK. A is contained in union AK, k running from 1 to n. That is, we say that the subsets AK covers A. The subset AK covers A. Okay, therefore a subset A of M is totally bounded if for every epsilon greater than 0, A is covered by finite number of subsets of M whose diameters are less than epsilon. In such cases, this A is said to be totally bounded. This A is said to be totally bound. Covers is the concept that already we know. Open cover and all. We have seen in topology in details. Okay. Also, we are using one basic theorem which we have already studied in our graduation level. That the metric space is compact. The metric space is compact if and only every sequence in M has convergent subsequence converging to a point in M. Okay, if someone wants to go in very detail, then you can refer a book by mathematical analysis by R.R. Goldberg. Here I will write the name. Mathematical analysis by R.R. Goldberg. R.R. Goldberg. Okay. Now we will come to the proof. Okay. Therefore, here we have seen the three definitions, rather two definitions: compact and totally bounded. Completeness we already know. A subset is compact if it is complete and totally bounded. And a subset A of a metric space is totally bounded if and only if that is covered by the finite number of subsets of the given metric space. Also, we are going to make use of this statement. The metric space is compact if and only if every sequence in M has converging subsequence, has a convergent subsequence converging to a point in M itself. Okay. Now, we will start the proof of our main theorem. Here, let me start the proof. Okay. Therefore, we are going to use the theorem which I have written just now. A metric space is compact if and only if every sequence has convergent subsequence converging to the point in the same set in M. Okay. Now here, what are the given things and what to prove? Let us recall. The subset S is given to us, which is closed and bounded, that is compact. Okay, and our aim is to prove that this space X is finite dimensional. This proof we are going to prove with the help of contradictory assumption, that is assuming X is not finite dimensional. X is not finite dimensional. Therefore here we will start with S is compact. The subset of a given nonlinear space is compact. Okay. Therefore, here may I say every sequence in S must have every sequence in S must have a convergent subsequence. Must have a convergent subsequence. This is our assumption. And the aim to prove is the nonlinear space X is finite dimensional. We will start with a contradictory assumption. Assume the contradiction. Now what will be a contradictory assumption? X is not finite dimensional. X is not finite dimensional. Right? This is our assumption. Now we will start by using a Riesz lemma in order to prove that whatever the assumption we have made is wrong. That is, somewhere we will get the contradiction again. Therefore, let us start with one element x1 in S okay, which is a compact, and let us create N1 as a subspace of X, as a subspace of X spanned by X1, spanned by X1, right? Then may I say N1 is proper subspace of X? N1 is proper subspace of X. Okay, now as N1 is a proper subspace of X, N1 is finite dimensional. Therefore, may I say N1 is closed. N1 is closed. By corollary number 2, we have seen in the last lecture, which depends on the proof of all norms are equivalent to one another. I will write the statement in short. If N is a norm-linear space, N is a norm-linear space, M is any finite dimensional subspace of N, then M is closed. M is closed. Okay, that is, if we have a finite dimensional subspace of a norm-linear space N, then it is closed. This is what a statement of a corollary number 2 we have proved in the last lecture. According to this, N1 is closed. Therefore, here the situation we have obtained is X is a norm linear space, N1 is finite dimensional closed subspace of X. Now we are ready to use Riesz lemma. Therefore, by Riesz lemma, what can I say? By Riesz lemma, there exists vector, unit vector, and the distance between the elements of N1 and this one element in X is greater than by epsilon. Therefore, may I say by Riesz lemma, there exists a vector x2 in S. Whenever I am writing x2 in S, what does it mean? Norm of x2 is equal to 1, because this is a subspace given to be a unit sphere. Or if it is with the second statement, it's only a closed bounded set, then by Riesz lemma, norm of x2 is equal to 1. Then may I say, there, as we are saying, there exists a vector x2. Therefore, distance between x2 and x1 is greater than epsilon. For the sake of convenience, let me select the epsilon value is half particularly. Epsilon lies between 0 and 1. In the Riesz lemma, we have seen this. Okay. Therefore, here N1 is a subspace of X. N1 is a proper subspace of X, and by Riesz lemma, we have found a vector x2 in S such that norm of x2 minus x1 is greater than 1 by 2. As this x2 is in S, means no doubt it is in X also. Therefore, what we will do? We will take another subspace N2, okay, and this will be generated by x1, x2 both. x1, x2. Therefore, the previous subspace N1 is one dimensional. This space will be of 2 dimensions. Okay. Therefore, by previous, again, may I say, this is closed subspace. This is closed subspace. Okay. Generated by x1, x2. Therefore, again, by Riesz lemma, there exists a vector x3 in S. That is, norm of x3 is equal to 1. Such that, what such that? Norm of x3 minus x2 is greater than 1 by 2. Okay. And just continue the process. Continuing in this way. Continuing in this way, may I say, there exists a sequence xn of elements of S such that, what such that? Norm of xm minus xn is greater than 1 by 2. What does this mean? That the distance between any two consecutive points of a given sequence is greater than half. And as we proceed to find out the distance between any two arbitrary points of the sequence, then the distance is again increasing. Why? half. Then it is not possible anyhow to have a that the sequence will be convergent. Okay, therefore this unit sphere has no convergence, as this is a sequence in the unit sphere with this restriction. Therefore may I say that this sequence of points on the unit sphere has no convergent subsequence. The sequence itself will not be convergent. It is not possible to find out the convergent subsequence. Thus this sequence of points, the sequence of points on S has no convergent subsequence, no convergent subsequence, which is contradiction to S is compact, contradicting S is compact, because as S is given to be compact, every sequence must have convergent subsequence, but here it is not true. Contradiction arises due to a wrong assumption, hence the assumption we have made is wrong. Therefore X must be finite dimensional. X must be finite dimensional. Okay, here we have completed with the proof of Riesz theorem. There is one small corollary here on Riesz theorem. I'll just write the corollary. The corollary says that if X is given to be finite dimensional, is X is given to be finite dimensional if the set S X in X norm X is equal to 1 is compact. This was obviously true by the statement we have proved just now. Okay, hence we will stop for today. I hope there is no problem with both the theorems, Riesz lemma and Riesz theorem. Thank you for watching the today's lecture.